As we said, we'll be presenting on the fracture repair for the Delaware River Turnpike Bridge. Just some brief history about the bridge itself. It's a jointly owned bridge for the Pennsylvania Turnpike Commission and the New Jersey Turnpike Authority, built in 1956. Carries a Pennsylvania extension over eastbound, westbound roadways over 3 local roads in Pennsylvania, as well as Amtrak Main Line and US 13, the Delaware River, obviously, and a local road in New Jersey as well. Has an ADT of about 41,500 vehicles a day, so a pretty hefty number there. In the morning, or sometime during the day on January 20th, 2017, a painting contractor doing some work out on the bridge for New Jersey Turnpike Authority came across this fractured top chord member. This is it's a pretty hefty section. This is W14 by 314, jumbo tension member on the top chord. There's a cross section showing the location of that. You can see it's it's a north deck truss top chord member here. Photo showing the location just near the river in Pennsylvania here. Slide also shows the road closures that were required underneath this particular 4-span unit, just for, pretty much done immediately, just to we weren't sure what was going on out there, so we wanted to take precautionary measures and get the local roads closed underneath there. Also gave us an opportunity to get some crews out there and some equipment. There's another photo showing on the near side the location of the fracture directly adjacent to one of the piers, and you can see the height here made things a little bit more difficult as well. It's about 70 feet or so off the ground, so not an easy task to get up there. Particularly concerning here was, in the early stages when we were trying to figure out what had happened. This particular span is one of 14 similar deck truss spans out of a total of 31 for the bridge, and it's a pretty significant length of the total bridge. Trying to figure out what had happened and why it happened was an immediate priority. During the initial inspection, we noticed a few things that had happened. Some of the stringers had slid off of their bearings a little bit. Some slight racking of the floor beams. The most significant thing we noted was member U18 prime, 19 prime, which is the top chord member directly adjacent to the fractured member. This was W14 by 87. Remember, the jumbo member next to it was a 14 by 314. So this member was very lightly loaded, essentially zero force member. Now it was basically holding up the entirety of that span. So the decision was made immediately by both agencies jointly to close the bridge. First immediate priority became stabilizing the structure. So within 2 days, we had designed, they had gotten plates out to the field, and we threw up a temporary bolted splice. This was meatball surgery, as we called it. I think we deemed it Frankensplice. It was very large plates, a high number of bolts. We just wanted to get this thing stabilized, not to fit perfectly, just to get this thing, kind of stitched back together a little bit while we figured out how the permanent repair was going to come together. Another initial thing we did here was take some samples directly from the location of the fracture and send them to Lehigh University for a battery of tests. So you can see them listed here: chemical analysis, microscopy. We kind of wanted to get as much information early on as we could to figure out what was going on here. One of the things we found almost immediately, or they found almost immediately, was indications of a misdrilled hole right at the fracture location that had been filled with weld material and then ground smooth at the fascia and then painted over. It was pretty much invisible until you cut a cross section through it. Another thing we found, the Sarpi V-notch tests were all over the map, essentially, with some results as low as 5 foot-pounds, and it gave us some concerns initially about the materials. It triggered a much larger materials testing program. M&M did some sampling, and those tests were sent to Lehigh. Additionally, UT testing was done for a lot of the tension members, and it's still ongoing or finishing up shortly here. Hands-on inspection for all of the critical members was done by GPI. One of the first steps here was to design and procure fall arrest towers. We had worked with Cornell on this. 8 towers were designed and installed directly adjacent to the fracture, basically 4 along each truss cord, the north and the south, or the deck truss, north and the south. For the foundations, we chose micropiles for a few reasons. One, the smaller footprint associated with the micropiles was a benefit, as well as it gave us the ability to kind of hopscotch over some utilities that were located out here in the area. Additionally, there was less excavation associated with these micropiles, and During the initial stages, we were unsure of the cause, and we weren't sure if pier settlement or pier motion was an issue here that led to fracture. So we didn't really want to go digging around out there. Costs were comparable, and we needed an immediate decision to get the ball rolling here. So that was done on 125. About 5 days later, we started to initiate the micropile installation. By 128, we had 3 rigs out there in a pretty small area, going 24/7. It started slowly, but as a contractor got his footing, really started to pick up a little bit. It created a mess out there. There was, this is just the drill mud, the drill water that was out there. It took a little while to get a handle on that aspect of it, but we eventually got that under control, cleaned it up a little bit for the people out there. 211, all of the towers were installed, and the hydraulic jacks were installed on the towers, because these towers, while they were fall arrest towers initially, would eventually be used for vertical jacking as well. So they were designed for both purposes. Essentially, they're just cranes sections that were stacked together. Process of figuring out how we're going to put this thing back together. Decided on a 2-step process. The first step being to vertically jack the truss back into place geometrically. Second stage would be to horizontally post tension the load back into the member, as well as just the lateral displacement that had occurred a little bit as well, and get back to geometry of this particular panel. And all the while, we're hoping that it would behave as our models had predicted. To the vertical jacking stage, which took place, initially we had evaluated the truss for the loads under jacking to determine if any of the members at the jacking points would be overstressed. We did come across one vertical diagonal that was showing some overstress, so we installed a cross member there to cut down on the unbraced length. That was about all we had to do with regards to strengthening of the truss under jacking, because we weren't really going to push this thing vertically up too much. This is a picture of them installing that member on the 21st. There was heavy instrumentation on the bridge in and around the location of the fracture. Andy gets 2 shout-outs in a row here. PB, WSP, was the engineer brought on board, consulting engineer brought on board for the instrumentation. Strain gauges, displacement, measuring displacement, things like that, so that we could watch the truss and how it behaved during both the vertical jacking and the post-tensioning. So the vertical jacking took place on 224. It was a 6-stage process initially, installed at all 8 towers. The initial process was to just bring all of those jacks snug tight to the truss, just to kind of maintain minimal pressure as we push this thing up. We were only going to be jacking from towers 3 and 5, which are the 2 towers on the north truss directly adjacent to the fracture. Stage 2 is removal of that stabilization splice, and then stages 3 through 6 involved, the vertical jacking process. Ultimately we settled on 2,900 psi of vertical jacking pressure that was broken down into quarters, and we were measuring this thing incrementally as we lifted it up. We had people positioned at all 8 towers, kind of taking a look at this thing, making sure it was behaving as we thought. The results were very favorable. We were able to lift the truss vertically about 1.44 inches, which was very close to the estimate, and got us pretty close to what it originally sat at vertically. As I said, it was only jacked from towers 3 and 5, and that was all we really needed. We just kept minimal pressure on all the other jacks. And as I said, we had people stationed at each of the towers on man lifts taking measurements as we went. Next came our horizontal post-tensioning operation. Some of the initial actions there included replacement of the truss cord. We decided to take it back to the far panel point from the pier up to the splice and replace that whole section. That was done on 227. The next day, the PT brackets were installed. Basically, that entailed encapsulating essentially the entire beam with 4 post-tensioning rods that we were going to basically pull this thing back together with. Post-tensioning was completed on March 3rd. Behaved pretty close to what we had thought. We determined that not much this system was a lot stiffer than we thought it was going to be. Not much stress was relieved out of the south truss, the truss that didn't fail or fracture. The north truss, models overpredicted the stress that we encountered there. And essentially, as you can see here in the yellow, we were measuring displacement physically with a tape measure up at the splice as we went here to figure out how much we were pulling this thing back together to get back to geometry. And these 2 graphs here kind of show what we were doing here. The target load was 1,500 kips, and that was the original dead load in that member. So we post-tensioned to that amount, and the whole while we're watching the displacement as we went here. The target as-built dimension restoration goal was 1.8 inches. We got to the low range of what our models had predicted at about 1.375. called it good enough as long as we got the load back in the member and called it a day. Once we completed that, we installed the permanent splice, which was we had bolted half the side up and left the other half ready to be drilled once we had it post-tensioned. Once that was installed, we depressurized the PT system incrementally, backed it all the way off back to zero, and the force transfer actually worked out very well for us. We only lost about 7% of that force in the member as it transitioned to the permanent splice. GPI was out there during the post-tensioning process, and some of the findings showed that what we had done seemed to work a little bit. The picture on the left here is directly after the event, at the critical finding, and before jacking. You can see how the stringer had slid a bit off the bearing, and it came back on. I know it's at the same angle, but it did come back on to the bearing pretty close to how it sat in its original position after the PT. Other repairs, I spoke earlier about that member, the W14 by 87, that U18 prime, 19 prime. We did not get any of the deformation out of that member, or most of it did not come out, I should say. So we ended up just strengthening that member with channels and basically created a coffin around the existing member. And that was about the largest of the repairs that were required other than the fracture itself. Once this was completed, we moved to load testing. Before we, and again, PB and WSP were heavily involved in this as well. Before we load tested, obviously, the PA side, we had been working on the New Jersey side to kind of calibrate, the load testing. We had sensors and instrumentation there as well to use that information once we got to the PA side. 8 overloaded dump trucks were used, positioned for maximum moment and shear, both moving loads and static loads. And there was very good correlation between the findings on the New Jersey side and the PA side after the fix. The truss responded linearly and elastically, which is what we were looking for. So the load test was deemed a success by all parties. So then both agencies essentially decided that we would be in a position now to open the bridge. On 3-9, the PT brackets were removed from the splice location. Radcliffe, which was one of the main streets that was closed on the PA side, was able to be opened. And then, the PTC and the NJTA worked together to remove road closures and MPT on their respective sides, and the bridge was reopened 10:30 p.m. on March 9th, less than 2 months after the fracture occurred, or fracture was found, I should say.
My part of the work I'm going to focus on is mainly the modeling and the analysis part of this work, and how we will be able to using model to assist our emergency response team in the field to put this truss together, those broken truss together. We got the call regarding this fractured bridge on a Friday afternoon around 3, and luckily for us, we have been worked on this bridge for previous assignment, so we got this model. With very minor tweaks and adjustment, we've been able to start an analysis right away. This is a 3D global model, and it's developed using CSI Bridge software. It's a linear elastic model. At the beginning of the job, we had the option to go linear elastic or go like more advanced plastic analysis to do time history to look into what really happened. But at that time, really for emergency response, this is not our focus. Our focus is to stabilize the structure to prevent any further damage. And so we went with this simpler and quicker response linear elastic model. The model includes most of all the primary truss members and most of the secondary members, including floor system. It's a composite concrete floor with stringers, and some locations even composite with the floor beam. And it includes the bearing expansion joints and so on. With this simple linear elastic model, but we want to make sure we capture all the possible scenarios, so we made a few tweaks. We kept the upper bound and the lower bound for its truss stiffness. So to make sure every step of the way we would fall in this safety bond, and we don't do anything like making the situation worse. With this model, we performed a stage construction analysis basically to simulate every step of the way of rehab, and including install additional bracing members to strengthen the truss, jacking at every step, 25%, apply 25% of force each step, and so on. Stage construction allowed us to track the behavior of the structure. And adding members, remove members, it's really a great tool. For emergency response job like this, it's a fast-paced response, but the first step and the foremost, the most important step is to calibrate our model to make sure we're using the correct results to guide our design team. And we went to a few steps. We looked at the as-built stress sheet, make sure numbers falls in the ballpark. We looked at the previous low rating results to make sure we capture all the updates, redacking, contract modifications. And we compared with the field measurements, that's the most important or accurate one we considered. For the fracture member, after we got some measurement back from the field, the gap between the two fractured ends opened up about 2.5 inches. And our model, the lower bound or the pinned model predicts going to be 2 3/8, so it's pretty close. And we have some kind of confidence on our model and to continue with this analysis. And along the whole process, we also compare our notes with the other consultants who's running independent analysis, including PB and Baker. And we found this process is really helpful and beneficial in such a quick response. In the following days, more information coming from the field. We got LiDAR survey. We also have live load testing. So we find out that based on the survey results, our pinned model, which provides less stiffness, really matches better with deformation in terms of survey. And our fixed model correlates better with stress. We haven't figured out exactly why, but that's some findings. It's interesting. And the two charts here compares our model prediction of the deformed truss bottom chord shape with LiDAR survey. The blue lines are the data obtained from LiDAR, and the orange lines are from our CSI bridge. For the upper chart, the chart on the top compares the deformation or deflection of the north truss, which is the fracture truss. So our analysis was less than what actually measured. And, but we're not that far off. At the worst case location at the center, close to the center, the truss is deflected about 3 inches, and our model predicts a little less than 2.5. And for the south truss, and I think our model, which is the truss, intact truss, and model fits really well. And there's a couple of outlier points on the measure points, mainly our consideration. Those are probably due to human error or when we're transferring the data. So again, you're looking at this meat-ball splice. It's not the most elegant design, but at that time, that's what we figure out to need to stabilize the structure. So within hours, we start calculation and see what's the status of that truss, whether it's stable. That's our main focus. And on the right-hand side, this figure is just what we did as a piece of scratch paper. We find out that the top chord adjacent to that fracture member is really overstressed by a lot. It only have half the capacity to carry the amount of force redistributed to this member. So what we were trying to do at that time is to get in touch with our field people to alert them to stay outside the drop line of the bridge because the bridge could collapse at any time. What we find out at that time is text messaging actually is the best way to reach out to people in terms of emergency response. Email, phone calls doesn't work. So we get this figure, basically text to our people, and at the same time, when we finally reach our people in the field, and we say, stay away from that member, it's already buckled, stay away from the truss. And our guy said, yeah, I'm standing right in front of this member, it's pretty bad. And it's deformed out of straight about 2.5 inches. That's what we find out. That's probably around at 8 p.m. that day. So it's about like 4 or 5 hours after the initial call. So what happened to this truss is basically it's a 4-span continuous truss. It's fractured at the center symmetrically. So it breaks into two separate units, 2-span continuous trusses. So naturally, we think the temporary support needs to be placed symmetrically on both sides of the spans. And based on analysis, we find out that the members adjacent to this fracture member is really heavily overstressed. They could fail at any time. If they do fail, what happened is we effectively lost the support from the center pier. So at a minimum, those towers need to be designed to be able to carry the amount of force in an event we lost the support from the center pier. That's how we determined the design force for the tower and the foundation. We also kept in mind that those towers will likely be used to push the truss or lift the truss up to its original location, and we want to provide enough capacity to do so. It's a two-stage jacking Dave has covered, and there's a couple of ideas kicking around. Eventually, we went to choosing this two-stage jacking. And the first we want to do is to lift the truss back to its original or close to its original position. Then we can do the splice. To determine the jacking force actually is quite complex. It requires iterative analysis because we're dealing with multiple constraints, multiple variables applying force at multiple locations. But at the end of the day, we simplify the process. We find out that if we just applying force at tower 3 and 5, that will give us approximately or good enough results. We also consider the effect of overrun in case we run up the jacking force by 25%. The most concern we have is putting too much force into the system that's already damaged the truss. What we don't want to do is applying force at a location which is not designed to carry this kind of force. And also, this is a pretty old structure, 60-year-old. And those rivet connection, we don't want causing any stress reverse in those old rivets. From the vertical jacking, as Dave has said, lifted the truss up about 1.44 inches, and our model predicted at those locations going to be slightly over 1.5 inch. So it's pretty close. We consider that acceptable and good enough. The second stage is post-tensioning. So there's two control methods we thought about. First is force control to restore the amount of force in this fractured member to its original state. And the other one is displacement control. We want to bridge the gap, completely close the gap created due to the fracture and bring the truss back to its original position. But based on analysis and field findings, we think that the truss, the fracture, especially the fractured one, is likely has sustained permanent inelastic deformation. So if we force them back together to close that gap completely, probably that's not a good idea to add in too much force to the system. So we choose the first one or the early one with force control. To guide us design of the post-tensioning, we also did a detailed finite element model using Midas Civil. This model includes all the PT brackets, splice plates, fractured member, and all that brackets we need. And we've checked the bracket or the members for two levels of loads. First, consider 10% of PT overrun, running 110% of 1500 kips. To check the members, we don't want any premature buckling happen during this process. And we don't want to see any yielding happen to any of the member or any of the element. The second level, we checked the fixture and the bracket for the strength of the PT bar. We want those fixtures to be able to develop the full strength of PT bar in an event of load overrun. So here just show you some of the stress levels. For the first level, 110% of PT force. We hardly see any yielding or overstress. The first two charts on the top. The two charts on the bottom shows on the second level. We just want to make sure there's acceptable of amount of yielding and nothing really significant occurs. So this is a picture of the splice plates and the member. You see a smiling face and two lines on the line on the left really is, they call it perfect. If we're hitting that line, which means we completely bridge the gap, we put the truss back in the position where it should be, and the darker line or the longer line on the left, actually there's a frowny face on top, which means we just hit the target of a force, we restore the force, which is predicted by our model, and we just by applying that force, we just met that goal, and we feel that's good enough.
The $100,000 question, well, probably more than that. Why? How did it happen?
It was a perfect storm of a lot of things. I don't think we ever know exactly why or when it happened for that matter. It was probably a combination of cold weather. The biggest factor was probably that mistral hole thing.
Right.
Just leading to all kinds of problems. But it was, it was a heavy tension member, a lot of things, overloading vehicles,
That misdrilled hole cost a lot of bridge maintenance engineers a lot of headaches.
Yeah, I'm sure it did. Because both authorities, a lot of headaches,
Oh, yeah.
Had to do that hands-on and you testing of every, tension member on the thing, looking for others, because you never know.
Right, right.
Once you could not see it.
Right.
Basically.
Yeah, that was my biggest issue, was a needle in a haystack. How would you ever find that?
Well, you kind of answered the question. I was going to say, how do you know that there is another location out there? Have you UT'd that there isn't another one out there throughout the bridge? I mean,
You can do your due diligence. Oh, I'm going to knock something. Looking for other locations. Like I said, we did UT testing of 100% of the tension members for those deck trusses. They did a more robust materials testing, which wouldn't find misdrilled holes, but would give you a sense of the material properties, because that was another inconsistency that we found. Even within that cross section, the material properties were inconsistent. And then a very detailed hands-on inspection as well. But again, with it being basically invisible, it's very difficult to be able to find anything there.
are you thinking about doing any like acoustic monitoring of the bridge? In other words,
That was
to verify?
brought up. I think that the final health monitoring program is kind of still being talked about between agencies. The instrumentation, I think Andy can confirm it, that the instrumentation is still out there, and it's kind of passively being monitored, with strain gauges and things like that. Acoustical monitoring was even talked about actually during the process here, just in case you heard anything else go bump in the night, literally, while we were out there. But that has been talked about, but I'm not sure what's going to happen.
Also, I know at one time there was a presentation down at Turner Fairbanks, the Federal Highway Training, about magnetic flux testing or something. It was some sort of Russian technology that they were presenting, where you can detect flaws they were using it in tendons, but by changes in the shape or geometry or any, I guess the steel, if it has any deformation or any change,
Sure.
like a drill hole filled with
Yeah.
a weld,
Yeah, there's
it
gotta
would
be some-
detect it. In other words,
Yeah.
it's just something, an instrument that you can run across.
Yeah.
But I guess UT would do the same thing for
Yeah,
you.
UT will kind of give you an internal picture as well, and at least hope to. I mean, you have to have that. That's all. It's only as good as your testers, though, and they brought out, not to get too detailed, but they fabricated plates with misdrilled holes, and they, some of them you could see, but they still wanted to see if the testers could pick them up as they ran their equipment over it. And we certified basically every, Baker was heavily involved with that, and certified every tester that they brought out there. To see, some of them were tough to find, and every tester they brought out could find them. So there's some confidence in what they looked at. They probably could say it was okay, but you never know 100% for sure.
Did the steel type play a part in this?
Yeah.
Because being at the year built 56, I noticed in the repair, those are riveted repair.
Yeah.
So it would have been A7, or is it A373?
It's called maintenance.
Yeah, maintenance, yes.
7 by supplied by Spectre.
And it was only used for a very short period of time, and typically not used for tension members either. It's
Right.
more brittle material.
Because A7 is not weldable.
No, it's actually,
It's not recommended weldable.
it's saying on the shop drawing on the plan, every sheet has that note, do not weld on this type of material.
Yeah, that would have been an A7 then.
Yeah.
And then the A373 was just the, if I can be so bold, the illegible weldable A7.
Yeah.
Because those, historically, I mean, I've had experience where you get a small indication and it'll blow up on you.
Yeah, I mean, and like I said, it was a perfect storm of men and material properties of steel were definitely played a part, I would say.
The preceding video was produced by the National Center for Pavement Preservation. More information can be found at tsp2.org. That's tsp2.org. Additional support provided by Michigan State University.